So actually, the title says it is going to be a talk on the relationship between a particular kind of Piotrovskaya semantics and Sequent calculus. Even though I did not get to attend it, I know that Uru has introduced it yesterday, but just to give you a brief overview, PTS or Piotrovskaya semantics is an approach in which we try to provide a semantic account of logic, which use the concept of proof as a semantic entity, and not concepts such as truth, which are used in model theoretic semantics. And what is relevant for my talk is that PTS is usually defined using natural reduction. And due to the fact that natural reduction is better behaved in intuitionistic logics, it is usually used to define semantics for logics which are intuitionistic in nature. So the original one was the original version of PTS, basic sense semantics, was given for intuitionistic logic itself, but we have some extensions. For instance, David Pimentel who extended it to linear logic as well. So, but it's usually the case that this is done for intuitionistic logics. I will show that if we do definitions of this kind by using sequent calculus instead, we get a very nice semantic framework for classical logic instead. So just explain the basic idea behind basic sense semantics itself. We first define a notion of atomic base, extensions for that base, and then we use them to define the semantic clauses of the semantics itself. So we start by defining atomic rule, which is just a natural reduction rule, which contains only atomic formulas. It's important that it cannot be closed under substitution. So those are fixed atoms, they have to be. Then we define atomic base as just a set of rules of this kind. I have also included rules that discharge rules, but we don't really need them in this context. But we define, okay, a set of atomic rules is a base. Then we define a notion of derivability for each base by considering the rules in them, which is quite straightforward. And then we define the extension of a base as any set obtained by adding new atomic rules to the base. So everything is quite straightforward. Just an example, but I think that most people here should be familiar with natural deduction. So this is an example of how deduction on the base works, but I won't stay here for long. And okay, what is the idea? Derivability in bases, or derivability from any set of assumptions, establishes what counts for a base to support an atom, to validate an atom. Once we have a notion of support for atoms, we extend them to other connectives as well, such as, for instance, conjunction, by defining semantic clauses which express what is meant to be the proof condition of the connective. And then after we do that, we just define logical validity by quantifying over all bases. So whatever can be proved in all possible semantic atomic bases is logically valid. And as I mentioned, the notion of proof is extended from atoms to logical connectives by semantic clauses. And it was originally expected, due to an insight of Keynesian, that we could use the introduction rules of the connectives to provide semantic definitions. Because essentially the introduction rules define a connective according to this rule, and the elimination rules are some kind of consequence from them. So it was expected that we would be able to provide a semantics for intuitionistic logic by just considering the introduction rules of connectives. That was shown to be not the case, because we have a semantic that works. It was proved by, it was introduced by Piotrovskaya. He uses a semantic clause, which is essentially based on the elimination rule for the disjunction. So this is basically just if you something follows from A and from B, then you already have it if you have the disjunction. And if we instead define the disjunction by considering something that looks like the introduction clause, so we have A or B, a proof of A or B. If and only if we have a proof of A or one of B, then this is no longer a semantics for intuitionistic logic. It's a super intuitionistic logic. And the same also holds for the definition of absurdity. So we cannot, like in critic semantics, for example, define bottoms in terms of non-satisfiability, because that leads to an issue. There is an alternative approach in which we define bottom as something which is appears together with atoms, and so can be included in atomic bases. And if we require bases to be consistent, then it works. But if we define a semantic clause for the bottom, then it does not work. I will not get into why this is the case. It's just an additional comment. But the point is that we cannot define bottom in terms of non-satisfaction. It does not work. And these are the semantic clauses. As I mentioned, we have a very basic one for atoms. Conjunction and implication, they are what one would expect. Bottom and disjunction are just as I mentioned. And it's important that for the entailment clause, we consider extension of a base. So, for instance, to show that A implies B, you have to show that in any extension in which I am able to produce a proof of A, I can also produce one of B. So this is how entailment and implication are defined. And again, once I define validity and entailment for bases, I can just quantify over them and define logical validity. Okay, so this is the semantics for intuitionistic logic. And as I mentioned, originally the clauses based on introduction were expected to use the semantics for intuitionistic logic, because natural deduction is harmonic when you consider intuitionistic logic, and not as much when you consider classical logic. On the other hand, when we consider sequent calculus, it seems like the sequent calculus for classical logic is more harmonious than the one for intuitionistic logic, which is basically a restriction of it instead. And quite ironically, we will show that, and this is the main result of this talk, that this harmony that appears in the classical sequent calculus, in fact, allow us to define a semantics that is only based on introduction rules and that works for classical logic. Okay, but first we must deal with some issues because we have to adapt the framework from natural deduction to sequent calculus. And due to some particular reasons, it's not as straightforward as it sounds. And there are two main problems. I will explain what they are. The first one is that when we consider natural deduction, so for instance, when we have a rule that concludes R from T, we are implicitly allowing some kind of weakening, because I am saying that if I get a deduction of T from any set gamma of hypotheses, then I can conclude R from the same set of hypotheses. But if I try to do this in the sequent calculus, because the sequent calculus, it explicitly establishes the context that is being used. So if I try to do it instead, I can only pass from T to R if the deduction depends specifically on the T and the Q. So the contexts are not arbitrary when you pass from proof to sequence. Another issue is that, once again, when I define deduction in natural deduction, there is some kind of implicit cuts being used because of how deductions are defined. And we don't have that in sequent calculus. We have an explicit atomic cut rule, explicit cut rule. And this also produces effects on atomic bases when you consider them. And there is a very simple example in the board. So if I consider a base with a rule concluding the atom P from empty set of antecedents and from P concluding Q, if it contains the appropriate instance of atomic cuts, then we can conclude, and it's down here, that we can conclude that T is derivable, but if you do not have atomic cut, we cannot, in general, conclude it. And the takeaway from this particular feature is that the presence or absence of cuts in the basis is semantically relevant in this context. Okay, so it is easier to handle context if we either have the cut rule for atoms, or if you have arbitrary context in the deducibility relation. But if we are if you don't have any of those, we have some issues in semantics, but we have to make a choice between doing one or the other. And just so that we show what is the contribution to the semantics of the cut rule. For now, I will define a notion of deducibility which deals with context. So it allows arbitrary context. And we consider now what happens if you have cut in the base and if you don't have cut in the base. I'm not sure I will have time to talk in all details that I wanted to about the difference between cut-free and cut-inclusive, but let's see. So I will use the definition that allows the use of arbitrary context, which is this one. So we require all bases to be closed, atomic bases to be closed under the atomic axiom rule. That gamma at is just a set of atoms. And sorry, this is the definition of base. So I just define a base as a set of sequent calculus from atoms, which contain all instances of the atomic cut rule with arbitrary context. After doing that, okay, I also define a notion of atomic cut and two notions of base, one which is closed under all instances of it, one which is not. And then now I define the divisibility. It is quite involved, but it's just the traditional definition of deduction sequent calculus, but we can use arbitrary context. I will exemplify this in the next slide. So for instance, I'm not expecting anyone to read this, right? So for instance, if I have the rule R1 and the rule R2 in a base, so suppose I apply R2 and get a deduction of Q from P and R. If the context of R1 is fixed, I cannot apply the rule R1. So it is a deduction to produce S because the context is fixed. But if I define the way I have defined it, we can apply it because the context here arbitrary, but the fact that the P disappears is included. But since there are extra R, it goes down to the conclusion. So again, it's just some kind of implicit weakening on the left and on the right that allows better handling of contexts. Okay, after we have defined derivability this way, we can provide some very simple semantic clauses for the semantics. So now instead of defining validity for formulas, we define validity for sets of formulas, just like we do in sequent calculus. We treat a set of formulas in one in the same context. Okay. The clause for conjunction is still the same, but the main difference is that now the clause for disjunction is what one would expect if the right introduction rules were used as a semantic definition. The clause for implication is the same. The clause for bottom, it is also different because remember that in traditional base extension, bottoms defined in terms of explosion, of atomic explosion. But now we have something that looks like some kind of weakening. In entrainment, I have something slightly more involved as well. But it's basically saying that if I pick an extension and I produce, so we have a consequence from A1 through AN, which concludes delta, if and only if, whenever I pick an extension, which produces A to get A1 together with some set gamma, A2 together with some other set gamma prime, etc. For all n, then I can use those supported contexts to produce one in which it will have this set delta and all the accumulated contexts. This is okay, even when I explain it is quite involved, but it is basically the same idea as before, but adapted to the sequent calculus context. This is in fact a semantics for classical logic. We have soundness and completeness results. And the clauses for disjunction and bottom, they no longer require quantification over atoms because I did not mention this, but I have to not only define disjunction in terms of elimination and bottom in terms of explosion, but I also have to use atoms just so that to make the definitions inductive. And this is no longer necessary here because we don't have quantification over atoms anymore. And again, this is the semantics for classical logic. How much time do I have? Just
you've got like 10 minutes. Yeah, okay. Maybe I should say like 8 if you leave 5 for questions.
Okay. I think I don't have time to comment on the difference there. Yeah. As I mentioned before, if there is a difference between atomic bases containing instances of atomic cuts and atomic bases which do not contain them. The traditional completeness strategy for such semantics, it has a very natural, straightforward adaptation if we consider bases containing cuts. But if the bases do not contain cuts, then we cannot And this is quite awkward because cut is admissible in classical logic. But as I mentioned, if we include it on the basis, it changes the semantics of the base. But even though it changes the semantics of the base, we can adapt the completeness proof so that we can also prove completeness for bases which do not contain atomic cuts. Okay, this once again is quite involved, but the basic idea behind Sank's strategy is that we map, so we fix a consequence, which is valid in classical connotation logic, in the logic which we want to prove completeness for. We map every subformula of it to some atomic formula, and we include rules which look like atomic versions of the logical formula, of the logical rules. And after doing that, we show that, and we call this a simulation base. And we show through a lemma that an atom is supported. So the atom to which a formula A was mapped in a base is valid in the base if and only if. So A is valid in a base if and only if I can derive the atom PA in that base. So the atoms to which we map a formula, they behave exactly as the formula itself. That's why it's called a simulation base, because we are simulating complex formulas to atoms. And we can show that the lemma I just mentioned, that the formulas behave just like the atoms they are mapped to. It works as expected when we consider bases with cut. And I will not enter the details of the proof, but this is better. But if we consider cut-free bases, then this particular lemma, which is the crucial lemma for the proof of the completeness result, it does not work. So we have to make some adaptations in order to make it work. And I think that I went really fast because I think the adaptation itself is the most interesting aspect of this proof. So now we create a base, atomic base, which simulates the non-atomic formulas. But now, instead of including rules which correspond to the sequent calculus rule, we include some rules which looks more like negative deduction rules, such for instance, one that passes from gamma at delta at PA and V to gamma at delta out PA. And in those simulation bases that contain rules which are not into the traditional calculus, we can prove, in fact, the lemma which allows us to prove completeness. And the proof of the lemma, it results in completeness because since the simulation base only contains rules that are basically atomic versions of the rules of the calculus, and we show that it has each formula behaves exactly like its atom, we are able to actually extract a proof from the semantics. But now we have a base which has rules which do not correspond to the sequent calculus rules. So how do we extract a proof if we are just guaranteed the existence of atomic proof with a different structure? And the point is that we can, so we extract a proof which contains rules of this kind, and then we complete them with a new instance of cut. So we extract, for instance, a proof that has an application of a rule of this shape, and then we extend the proof to one which contains cut. So the inclusion of rules which are not rules of the calculus does not prevent the extraction process from working. So I think I might have went way too fast in the proof, but okay. In short, there are two ways of proving completeness in this setting. If we have cut rules for atoms in the base, then we can just use this strategy. There are no issues. But if we consider only bases with, if we allow bases to be cut-free, then we have to, during the proof of completeness, extract some kind of weaker proof and then include instances of cuts, which are pushed upwards in the proof. So it's not in the atomic level, but it is in the level of the proofs we obtain. We introduce them at a higher level. And okay, if you, and I think I should go back to the semantics also before I talk about this point. So if you look at the atomic support clause, we only consider sets of atoms which were produced from an empty set of antecedents. And we don't, in general, have to take into account left context, only right context. So we only have one context for each of the semantic clauses. And this is only allowed because we are in classical logic, and in classical logic, we have a nice interaction between context on both sides. So classical logic allows simplifications, which in turn allows the semantics to be this simple. But if we want to go to substructural logics, we cannot count on these, of course. So one thing that we are doing for future work is to expand the definition. So now we consider also deductions which are non-empty antecedent, but now we put this antecedents as some kind of indexing of the antecedent, which is something that has been done before in, for instance, PTS with meta reduction for linear logic. But it's not new, but it can be used in the sequence calculus setting as well. And in this context, just like the cut rule has semantic content, and so it produces some semantic effects in the basis, it is also natural to expect that all the other rules, such as weakening, contraction, etc., will also play some kind of relevant semantic role in the semantics. So, for instance, I think it's very reasonable to expect that we will have to consider simulation basis clause under atomic weakening, atomic contraction, etc., for the semantics to work. So that's it, but I want to first mention some things on this. There is some interesting aspects of this because it looks a lot like sequent calculus, and in fact, the semantics, it mirrors a lot of the behaviors expected in sequent calculus, but not all of them. For instance, even though it might seem like this is very close to sequent calculus, we cannot just restrict the context to one antecedent of the intrinsic logic. So this is at the same time something which is quite close to the original calculus, and I think that is so new that it has very new behaviors. And okay, after this brief comment, I think I'll finish here. Thanks.